Today, we're looking at different methods to calculate and display the speed of your model locomotives. And you may ask, why? And there are serious reasons and maybe less serious reasons for tackling it. Let's look. Firstly, you may simply see it as a technical challenge. Am I up to it? Can I design it? Can I get it to work? Am I good at problem solving and so on? It's an end in itself. Or you may simply see it as a bit of fun, an interesting thing to do and to have. You may have a serious reason for it. If you're in a model railway club exhibiting, it'd be nice to have a feature on your layout that displays the speed of a loco as it passes by. We have that already in one of our WASAG exhibition layouts. Or you may approach it from the point of view of having accuracy. We work in scales, and that involves also scale speeds. Too many locos, in my opinion, at exhibitions run far too fast. You see shunters running at express speeds and so on. And that's fine to satisfy maybe kids at an exhibition, but you may want to have a much more accurate representation of the speed of particular locomotives. Or you may have use for it in DCC. If you have consists of double headers, treble headers, when you have two or more locomotives pulling a long section of wagons, particularly in large layouts like American layouts that are huge, when you're pulling 20, 30, 40 coaches, you've got two or more locomotives doing it. And you have to set those two locomotive speeds to accord with each other. When you set the knob to 1/3 speed, they should both go at the same speed. Otherwise, one wheel's going faster than the other and the wheels slip in one of the locomotives. So you have to tweak them to both respond exactly the same. And this will be very helpful in doing that. Or some locomotives, particularly ones used for shunting and so on, should have maximum speeds. And you can set in DCC to ensure that no matter how you turn the knob, you cannot exceed the maximum speed for that particular locomotive. I'm not going to go into what typical speeds for each locomotive are. There's a whole range, as you see here, depending on whether it's freight trains, express trains, and so on. Their hardware makeup and so on, but you know what's right for you. So, to calculate speed, we need two things. We need to know the distance we've covered and the time it took to cover that distance. That's all we need. Two measurements, and we can calculate from there. So what we're going to discuss now are how do we get those measurements of time and distance, and how do we calculate and display them. Lots of methods, from the stopwatch to commercial ones to various ones I'll look at shortly on how we can have DIY versions of them. And we'll look at all of these. At its cheapest and simplest, if you've got a mobile phone, it may already have a stopwatch app on it, and if not, you can download, as you can see, loads of apps of different kinds, where you can actually do your own timing, like a stopwatch if you haven't got a stopwatch, and you can watch the time it takes to go between two markers. And once you know that distance and you know that time, you can go into the calculator function of your phone, or download a calculator, or go online and work out the speed. The benefits of that is it's free. If you've already got a phone, it's free. The apps are free to obtain. The software to calculate it, freely available. Downside, it's not great for precision because it depends on how accurate you are and you hitting the button to start and hitting the button to stop. And of course, the shorter the sample, then the more that comes into play to give you inaccurate readings. And it's only when you see it on your phone. So the rest of the people can't see it. So if it's designed to be shown to the public, this is not the ideal method, obviously. You can go onto the internet and you can get speed calculators. There's one there, free to download. There's another one, and at the top you'll see the URL to get it. It's got fixed distances, though that's the only problem. As you can see, we can tick which scale we're working on, that's fine. That covers most of the members. But the distance are in fixed amounts, which is fine if you're able to have fixed amounts on your layout, if you're able to set markers. But if you want something different, then this will not work. And all you're going to do is feed in the distance you covered by clicking one of these buttons and then entering up here the time it took to cover it. Click the calculate button and it'll tell you the speed. So it's simple to use. We have to scale it depending on what gauge we're using. Because we know the distance and the time, what we don't know is what scale we're working on. To calculate that back up to the actual scale speed rather than the actual speed you've measured. And you can see there we have 00 at 1/76. Although interestingly, the P4 boys, S4 boys, I've got 176.2. Somebody mentioned to me already that some of the commercial units have got discrepancies in speed for the same time and distance. Two reasons, there's one of them, a slight discrepancy depending on whether you're doing 00 or P4 and so on. Even though they're both 4 mil, they've got a different ratio and will give a slightly different answer. Lots of the American hardware to do this works on 176.2 rather than 176. And the other reason is the mathematical method that's used to do the calculation because of rounding errors and so on. So we want to get the results expressed in miles per hour, maybe kilometers per hour, but our layout isn't measured in miles. It's measured in inches or millimeters. The distance between 2 points will be so many inches or so many millimeters. And it won't be in hours, it'll be in seconds to travel that part. So we have to do some calculations to get us between what we measure and what we display in miles per hour. So let's start by looking at what's available commercially. The first of these commercial units then is the AccuTrack. As you can see, it can handle HO, 00, and N scale. Works from 2AA batteries. The unit sits across the track and has 2 infrared beams, one at each end. and then the loco breaks the beam as it enters and breaks the beam on the way out, and it measures the timing over that distance. I'm not certain of its accuracy over such a short piece of track, but it is portable. This is the offering from Train Control Systems. Can't find a UK stockist for it. It's got a 3-digit readout, and it works on the basis of 2 LDRs spaced apart, light-dependent resistors. I'm not, again, certain about the accuracy of that, because if that's the sensor and the loco's coming from that direction, it depends where the light source is. If the light source is behind the loco, it'll cut off quicker. If the light source is the other side of the loco, it'll cut off later. So it's not particularly accurate, in my opinion, on when it actually triggers. This is a DRM SPC 100. As you can see, it's a self-contained unit with the detectors already on the module and a digital readout, 40 quid. Again, I'm not certain about the accuracy of such a device, given the fact that the sample's taken over a very, very short distance, something like 3 to 4 inches. Plus, we may want to be measuring the speed over one complete circuit of a loop. And that may involve gradients up and gradients down and so on, working its way through points, etc. And we want to work out the average speed of a circuit. And that would not be suitable in that kind of situation. If we're looking for something that's spaced out a bit more, there are a few options. Here's the one from America at just over $200 with fixed sensor spacing, but only slightly further spaced than previously. Digital readout and buttons to give you options. Still not ideal. Or this one for sale on eBay. Uses 2 infrared modules with longer leads, so you can be spaced quite a bit apart if you wished. And a 3-character display. Uses infrared modules. And then finally, in the commercial side is a speedometer built into a truck. Not cheap. As you can see here, it works on the basis of having a beam directed through the spokes of one of the wheels. And as the wheel rotates, it breaks the beam, and you can count the number of times it's pulsed, and you know the size of the wheel, so you can work out how much it's traveled per pulse, and from that you can work out the speed. Again, I'm not certain just how practical it is, because by definition it's moving, and if you want to look at it, you've got to be looking as it goes along. It doesn't seem more of a gimmick, possibly, but if you've got a use for it, and of course it's portable, you can put it onto any layout that's got the same couplings. Right, so much for commercial units. We'll look now what we can do ourselves, starting with something that's free. Most of you may have watched the Hornby series. And one particular week, a hobbyist had worked out the Loco speed by video recording a Loco move between 2 points, and then took that video clip and put it into video editing software and used it to determine the speed that his Loco was traveling in. So let's see how we do that. Step one is to get a piece of track and lay out markers at each end for the length you want to measure. In this case, it's 1 yard from the Loco coming rightwards to here until it gets to the edge here. Step two is to record a Loco on that piece of track. So we now have a video recording of the Loco travelling between the two markers. I can check it out in OpenShot video editor. I can bring in the video clip that I've just taken, pop it into what's called the timeline, and you'll see here the time of each frame. So if I now move the Loco through the video clip until, in single step, until it reaches the marker, take a note, it's 3.11 seconds, and then run the Loco to the other end, and when I get close, single step until it hits the marker. Take a note, that's 10.21 seconds. So it travelled 36 inches in 7.1 seconds. Now that we have some measurements, a distance and a time, if we're not going to use the online calculators, how are we going to work out and display the speed? So we have to work that out, not just for this example, but when we do our own hardware that's coming up later. So let's look at the formula that gets you to scale speeds. We're going to use initially a spreadsheet to show it. We know that speed is distance over time. We know that in model railways, we're probably measuring inches rather than feet and yards and miles. And we know the time taken to cover that distance is probably measured in seconds, or parts of an inch or parts of a second. So if we create a spreadsheet and the first entry is the distance between the samples and the time it takes to travel between those two samples, then the speed is distance over time, inches over seconds. If we divide the value by 36, we get the speed in terms of yards per second. If you multiply it by 60 and 60, Then we get the yards per hour. That's yards per second multiplied by 60 is yards per minute multiplied by 60 yards per hour. So now we have the speed calculated in yards per hour. We can divide it by 1760, the number of yards in a mile. And the answer we have here now is the miles per hour. That's miles per hour real speed, but we're talking about scale speed, so you'd have to multiply that figure here by the scale you're using. So for example, if it's 00, we multiply it by 76, and the scale speed for covering 1 inch in 1 second is roughly 4 miles an hour. Can we simplify that? Well, we can say the formula is the inches divided by 36 divided by the number of seconds, and then multiplied by the 60 divided by the 1760 multiplied by the 76. Or we can simplify that to say that all of that put together comes out at 4.3. So if we take the inches, divide it by the seconds, multiply it by that factor, then we'll arrive at the scale speed for 00. So we can simplify all this down to this piece here, a spreadsheet where you enter the number of inches in the test, the amount of time taken to conduct that test, divide that by that, multiply it by that, and you get the answer. So we get a simple formula with only 3 factors: the distance, the time, and the scaling. So that's the spreadsheet for calculating miles per hour. But what if you're working in kilometers per hour? Well, so that's the formula for calculating miles per hour. And we can do the same thing for kilometers per hour. In this example, we have covered a meter in 6 seconds. So the speed is that, millimeters per second, divide by 1,000 to get it into meters per second. If we can cover that amount of ground in 6 seconds in meters, then it'll cover times 60 times 60 in an hour. So it's doing 600 meters per hour. Divide it by 1,000 to get you back to kilometers per hour. That's real speed. Multiply it by whatever gauge you're working in, 00 here, multiply by 76, and we get the scale kilometers per hour. There's the formula, which again can be simplified down to get your distance in millimeters, get your time in seconds, divide one by the other, and multiply the answer by that factor. Okay, let's look at the actual spreadsheet now. Here we have the spreadsheet then, the actual spreadsheet. I can put in any values I want. 2 feet at 10 seconds is 10 miles per hour. 2 feet at 5 seconds, 20 miles an hour. 36 inches a yard at 7 seconds. A yard at 6.5 seconds. Or 700 mil at 6 seconds. 700 mil at 3.3 seconds, and so on. So with this spreadsheet, we can put in any value for distance in terms of millimeters or inches, put in the time, and you have the scale speeds. The only thing you have to change here would be the multiplying factor for N gauge or any other gauge. Now that we know the calculations, we can go back and look at the example of the figures we extracted from the open shot video clip. I now know it took 7.1 seconds to cover the 36 inches. We go back into my spreadsheet and enter 7.1, and it was 21.8950064 miles per hour. Well, we've looked at the commercial offerings. We've looked at two ways of doing it without any extra hardware, just using your phone or using your webcam in conjunction with free software. But we're Merg. We want to do things and build things and be able to fiddle about with things. So we're looking at homebrew equipment. So what have we got to start with then? Got a few offerings to look at next. The first one I want to look at involves lasers. Why? Because lasers emit a very fine beam. And if you break that beam, you get great precision. You know exactly when the beam is broken. There's no dubiety about ambient light or light from different directions. It's very, very precise. And for that, we're going to use the laser and phototransistor that was used in the laser totty. A laser emitter sends a beam across to the phototransistor, changes the light level that goes into the PIC in this particular example, and it began life in Vero board. It's now a pocket money kit on printed circuit board. But we don't need all the PIC. We're going to feed it into an Arduino. But we will use the laser and the phototransistor and the idea of breaking a beam. So to do that, we need two components. I'm using a Uno here because it allows us to plug in a shielding top. So two components, get the Uno, plug in the shield, and now we're able to present graphical information. That's what's used in EasyBus, as you'll see up there, that approach. So we're going to program that, and we're going to fit it onto the same piece of board that we saw earlier and have some laser detectors at each end. So it's like that. The laser is normally a 5-volt laser. I've got it working in 3 volts to cut down the current and make it longer life. And I haven't gone to the bother having it switched like I did with the pocket money kit, because it's not going to be on for too long at any one time. If it was, we would have to probably arrange some switching of the laser to save laser life. So we have 2 of them, one come in the left-hand side, one come in the right-hand side to give us the 2 detectors. So apart from the Uno and the LCD shield, 4 components for one side, 4 components for the other side. So the hardware requirements are quite slim. That's the approach. in the code, obviously it's not the Arduino code, you wait till it passes, the Loco passes the first trigger, and you start the timer. And in my case, I'm displaying an arrow that lets you know it's past the first timer and is progressing. The program then waits until the Loco hits the second trigger, and it says how much time has elapsed. I now know the distance between my two detectors, 36 inches. So I know I've got a yard of distance, and I now know I've read the amount of time taken. So I can use the formula we looked at earlier to calculate the speed and then display it on that LCD screen. I've written it so it will do N gauge and 00 and reads out in miles per hour. I could add a second switch if I wanted to give us the option to have two formula built into the program, one to calculate for miles per hour and one to calculate the speed in kilometers per hour. So let's see it in practice. Okay, this is the setup. You've got one camera pointing at the board, another camera pointing at the LCD screen. So let's put on the power. And we're currently looking at reading 00 speeds. Put on the power supply, put the Loco on the track, connect the power to the track, and as it passed the first sensor, you'll see that it showed an arrow. Past the second sensor, and it reads off the speed. Increase the voltage. Passes the first sensor, indicates it by an arrow. Second sensor, speed. Same again. Reading the speed. So the switch to N gauge, same voltage. "100 miles an hour, whoa. Bit more realistic. "30 miles an hour. A variation on this is what we have in the WASAG demonstration layout. Instead of the Loco passing 2 points, it passes the one detector twice on the circuit round the layout. You can see a yellow arrow there that points to the detector in question. It's using the TOTI2. In other words, it's the current detector. And the code, as you see, is simply wait for the first time on the way around, start the timer, and then when the second time comes round and triggers it a second time, you measure the time taken. Simple as that. Calculate the speed and display the speed. In our particular case, we're using large alphanumeric displays up the top right of the layout there. So apart from the AccuTrack that you sit over the track, so far we've looked at static. We mount detectors on various parts of the track. What about having some that are handheld? You just point it at the Loco as it comes towards you. and take a reading. I had a look at a couple of those. And the first one I looked at was our old friend, the Ultrasonic Module. Very cheap to buy. Comes complete with a transmitter and receiver head. It emits the ultrasonic, bounces it back off the object, and receives back to the measuring head. What's the same principle as before, bouncing it off a loco as it approaches. You'll see a line there marked trigger, and that's what starts the transmission of the ultrasound. And then the echo is when it bounces back from the locomotive body. There it's there. Very few parts in this case, just the Uno, an LCD shield, and a couple of wires that take the power to the module, and a couple of wires that take the trigger and echo back from the module to the Uno. Simple to make and build, and that's it mounted, looking along the track at an approaching loco. Its good points are that it's a very low current device. It's also got long range, and it's handheld, so it's portable. You can take it to any layout. Downside is that it's got a wide angle of spread. And the further away you go, because the wider the spread is, and that means that you get reflections from other static buildings on the layout. You're not focused narrowly on the loco approaching. If you've got a building to the side or a signal or whatever, then it's going to echo back. So it's not great for smaller gauges. Probably quite handy for O gauge and layouts that have got wide expanses to allow for that. When we're working from reflections, then the code is slightly different, as you can see there. Normally, we know the distance and we're measuring the time it took to cover that distance. This time round, we know the time we're going to wait between readings and working out the two distances involved. So the code is going to be, take your first reading, signal will bounce off the object and back, and you can note that time it took to do that. Then you wait your fixed time, you know the time you're going to wait, and do it again. Take a second reading. The loco is now closer to your reading head, and therefore the time will be shorter. So we now have two time readings. We take the lesser from the larger, and we now look at the difference. We have to divide by 2 because the time it took is actually half the time of the reading, because half the time was getting the sound to reach the loco, and the other half was it returning again to the echo. So the actual time is only half of what the readings are. So now we have the fixed time, and we now know the amount of distance it covered in that time, and we can do the calculations and display as normal. That's what we use for the ultrasonic and also for the laser detector I'll be looking at next. And lastly, we'll look at the laser-based handheld detector. The problem we said with the ultrasonic version was the wide angle, whereas the laser, we know, is a very fine focused beam, and therefore is not subject to distractions from buildings and scenery and so on your layout. So how do we implement that? Well, you can buy a module called a time of flight sensor. As you can see, only 4 connections to make it work. That's all that's required. And tiny size. That's the one I'm using. And you can just see the black rectangle there that houses both the laser emitter and detector in that small case. Only requires 4 connections to your nano or Uno or whatever device is going to control it. 2 wires to take the power. You can see the red and black there. And 2 wires that are used for communication between the module and your Arduino. In this case, it's using I2C bus for communication. That's a short clip of it in action. As you can see, it's got a very precise measurements. It's measuring in millimeters. Let's have a quick look then at the technical specification for this module and some of its features. As I mentioned earlier, very small size, roughly 5 mil by 3 mil by 1 mil, tiny little module on that PCB that works on the I2C bus. And it gives you the unique address of that particular module. Very low current consumption. But the biggest issue right now for us is this one. Unlike many other modules, it works on a voltage between 2.8 and 3 volts only. And we want to interface this to the Arduino. This can cause problems for us. The module itself wants to run on 2.8 to 3 volts for power. We can overcome that with voltage regulation and so on. That's easy. But the data going between the module and the Uno or the Nano, whatever, are different voltages. The output coming out of the laser module are pulses where the logic is 2.8 volts or 3 volts. Whereas what's coming in and out of the I2C from the Arduino is at 5 volts. So we can't just directly connect the two together, not without problems. So we have to find some way of connecting 2 modules that have got different voltage levels together. Doesn't only apply to this particular module. More and more nowadays, you'll find modules that work on 3.3 volts. Indeed, some of the micro controllers also run at 3.3 volts, not a problem. But you might want to be regularly connecting 3.3 volt devices to 5 volt devices. So we have to have some way of doing it as simply as possible. And that's done for us by using what they call logic level shifters. And we can look at what we used in this project. And here we have an example of a logic level shifter module. Relatively cheap. You'll see it's bi-directional. In other words, we have pins down the left hand and the right hand side of that PCB. Any logic changes on the left hand side are reflected on the right hand side, and vice versa. Any changes on the right will be reflected on the left. Like this. We're trying to connect together 2 devices, one with a lower voltage and one with a higher voltage. I'm just using the example of a 3.3 volt module on the left-hand side and a 5 volt module or circuit on the right-hand side. So what we do is we connect the low voltage to the pin that's marked LV. We connect the higher voltage to the pin marked HV. And it now knows that any changes that occur on L1 will be reflected onto H1. Any changes in H1 are reflected into L1, only at different voltages. L2, for example, might go from 0 volts up to 3.3, and H2 will see it rise from 0 to 5. Similarly, if H4 went from 0 to 5 volts, L4 will go from 0 to 3.3. So we've got total protection between the two devices or circuits. How do you apply that to ours? That's our module. We're taking a 2.8 volt supply to feed the module on the left-hand side, but also feed the LV pin. The Arduino's 5 volt pin comes out to the HV of the level shifter. And now any changes in SDA, SCL will be reflected across the device at different voltage levels. We've solved the problem. So there we have it. We've looked at a number of ways to measure and display locomotive speeds. The code for the laser module is very similar to that for the ultrasonic. Take two readings of distance, spaced by a defined amount of time, and you can work out the speed and display it. Just to remind you of its usefulness for DCC, for those of you who use consists or double headers, I found this particular document very, very useful. You'll see the URL for it at the top. And also, for those who don't have double headers, don't forget your maximum speed using CV5. And that's it, folks. You may or may not have a use for it, or you may just want to play with it. Either way, have fun. Are there any questions, comments, or suggestions?